Welcome back. I'm really excited about what we're working on today, which is an introduction to functions. So I've created a quick map to give you a sense. You can wrap your head around what we're going to cover. We're going to start by talking about what relations are and what different types of relations exist, and then we're going to talk about a specific one called a function. We're going to learn function notation. We're going to learn the concepts of domain and range, which is going to involve learning some interval notation. We're going to look at how functions can be subject to transformations on the plane, which means we can stretch them and move them and kind of change how they look on a graph. We're going to look at function composition, which is taking more than one function and combining them in different ways. We can add them, subtract them, multiply them, divide them. We can put them inside each other, all the good stuff. And then finally, we're going to look at what are even and odd functions. And as we go, we're going to look at examples of each of these. We're going to cover this stuff, then we're going to have a check. We'll do a bunch of examples, and then we'll cover these two concepts. We'll do a bunch more examples. I really love this particular topic for a few reasons. One is that in order to do calculus, you need to know about functions and you need to know about limits. We're not going to cover limits today, but this is one of the most important steps to take to prepare you for being able to learn calculus, which is cool. The other thing that I really like about functions is it's a lot of pure algebra. It's a lot of practice of expanding brackets, simplifying algebraic fractions, all of those things that once you get the hang of it, and I've hopefully got the hang of it, everything just is following rules. It's like doing lots of little puzzles. There isn't going to be much of a requirement at all today for any creativity, any problem solving. There are no worded problems at all. It's just going to be pure math the whole way. So I'm excited. I hope that you enjoy it too. Let's jump in. So I want to start with the question, what is a relation? In algebra, a relation is any rule that connects at least two different variables. So here we have examples of relations. This is a relation, it connects x and y. This is a relation, it connects x and y. This is a relation, it connects x and y. This is a relation, it connects x and y. This is a relation, it connects x and y. You should be able to see a theme, a bit of a pattern running through here. All of these look different. None of them look the same, but these are all examples of relations which have two variables, x and y. Relations associate sets of values. Now I'm using these weird terms because relations are very abstract concepts, and what that means is we can talk about relations with numbers, that's what we're going to do, but we can apply the same concept to all sorts of things. A relation could be in a computer database, and you could have a relation that connects a user to their user information or to their network of connections. All of these concepts are versions of what we're talking about, a relation. But let's stick with numbers. So we'll take this example, x squared plus y squared equals 25. Hopefully you recognize that this is a bit of a Pythagorean triad. So we have a pair of x and y where the squares of the two values add to 25. So x and y are related by this rule. So we can have some easy examples. X could be 3 and y could be 4. There are actually a lot of examples that could work. X could be -3 and y could be 4. X could be 3 and y could be -4. X could be -3 and y could be -4. When we square them, those pairs will all add up to 25. Similarly, suppose we said, but we want to know when x is 1, what is y? Well, then we can say 1 squared plus y squared equals 25. Rearranging this a little bit, we're going to get y squared equals 24. So y will be plus or minus the square root of 24, which will be plus or minus 2 root 6. So if x equals 1, we could have y is 2 root 6. We could also have x equals 1 and y being -2 root 6. So for a given x value, we can find what is the y value that will make it work. So our relation is a rule that allows us to take an x value. So this is a set of x values. And from our set of x values, we can pick one, and then we can figure out which y value that x value corresponds to. And we can see in this case that that x value, x equals 1, has two possible y values it connects to. It's got +2 root 6 and -2 root 6. Okay, but what if x equals 10? Well, we have a problem then, because if x equals 10, then 10 squared plus y squared equals 25, which means y squared equals -75. And this is a problem because we can't square root -75. And so what we get from this is that there is no y value that will work if x equals 10. So if x equals 10, we have a problem. This means there are some x values which do work and some x values which don't. And we're going to come back to this concept very soon, and we're going to talk about the domain of a function. But we're not up to functions yet. We're still on relations. So I just want to use this visualization here. We can see for the function that we were looking at, we have a set of x's and a set of y's. And you can see if x is -3, then y could be -4 or +4. And if x is +3, y could also be -4 or +4. So from one x value, we can go to two y values. And for each of these y values, we can get to each of them from two different x values. Let's have a look at this way of analyzing the x's and the y's, the inputs and the outputs, and look at some types of relations. All relations fit into one of four categories. We have many to one to many, or one to one. Let's break down what each of these are. In a one-to-one type of relation, anything on the left-hand side can only connect to one thing on the right-hand side, and anything on the right-hand side is only connected to one thing on the left-hand side. One to one. If we have one to many, it means that anything on this side can connect to many things on this side. It doesn't have to, but it can. However, anything on this side can only be connected to by one thing on this side. One to many. The opposite of one to many is many to one. So anything on this side can only connect to one thing on this side. But things on this side can be connected to by more than one thing on this side. And then, like the example we were looking at a second ago, many to many means that something on the left can connect to many things on the right, and something on the right can be connected to by many things on the left. So here are the four basic categorizations of types of relations. And we're going to be interested in two of these in particular. They're going to be many to one and one to one. The ones that end in one. Let's visualize some of these more graphically for a second. A circle is a great example of a many-to-many relation. And the reason is, if we take one x value, this x value can correspond to multiple different y values. And if we take one y value, this y value can correspond to multiple different x values. For this x value here, we can take a y value up here, or we could take a y value down here. For this y value here, we could take an x value over here, or we could take an x value over here. So one y value could give us two different points on the circle. One x value could give us two different points on the circle. This is many to many because one x value can give us more than one point on the curve, and one y value can give us more than one point on the curve. This is a relation. Now we have a many to one graph. And so what that shows us is that for any x value we choose, we will only ever get one corresponding y value. But if we choose a y value, we could get more than one x value that correspond to it, right? So many x values could give you the same y value, many to one. Here's an example of a one-to-many graph, and you can see it's the same one. I've just turned it sideways. So one x value could give us many y values. And finally, one-to-one graph is a graph where one x value gives us one y value, or one y value would give us one x value. Now, there are tests that we can use here. I'm going to explain the test in two ways. Firstly, I'm going to talk about a horizontal line test. You're going to spend most of your time thinking about a vertical line test, so I'm going to finish with that. This relation here passes the horizontal line test because no matter where we put this horizontal line, it only touches the relation once. This relation also passes the horizontal line test. Wherever we put the line, it only touches the graph once. This relation fails the horizontal line test because there are places we can put the line where it's going to touch the graph more than once. This one also fails the horizontal line test because there are places we can put the line where it touches the graph in more than one place. Anything that starts with many is going to fail the horizontal line test. Now, we are more interested in the vertical line test. The vertical line test will be failed by anything that ends in many. So this many-to-many graph, this circle, fails the vertical line test because I can find somewhere to put the vertical line where it's going to touch the circle in more than one location. This is a many-to-one graph because it's to one, it will pass the vertical line test. There's nowhere I can put this vertical line that it will touch the graph more than once. Here we have a one-to-many graph. Because it's too many, it will not pass the vertical line test because there are places where one x value corresponds to more than one point on the graph. And finally, this is a 2-1 type of relation, and so there will only ever be one place that it will touch a vertical line. The vertical line test is a really quick and easy test that you can use to tell if a relation is a function. Let's quickly summarize. Functions are many-to-one or one-to-one relations, which means they are going to pass the vertical line test. And it's really important that they pass the vertical line test. We don't care about the horizontal line test when we are identifying if something is a function. Some functions will pass the horizontal line test and some will not. The vertical line test is the one that matters. If a function is one-to-one or one-to-many, it will pass the horizontal line test. If a function is one-to-one or many-to-one, it will pass the vertical line test. We're interested in it ending with 2-1. If a relation passes the vertical line test, it is a function. Hence, a function is a relation which is one-to-one or many-to-one. In other words, whatever the input, there is never more than one output. Here we're saying the same definition in many slightly different ways because you can be asked a question in many slightly different ways, and you need to know that all of these things are true and they're all essentially telling us the same thing. Now I want to explain how we write functions. What is function notation? Here are some examples of functions, and they should all look familiar to you from studies you've already done. Here we have a linear function. Here we have a quadratic function. Here we have something that's a little bit fancy, but this is also a function. All of these, when written in function notation, will look slightly different. This side is the same, but instead of y equals, we name the function. So this is a function named f, and the function f has a variable x. We've named this function g of x, and then we have h of x. You could have a function with more than one variable, but I'm not even going to touch that because we've got a lot to cover. We're going to keep it simple. Our functions have just one variable. We can evaluate the function at a specific value of the variable. So this is the function f of x, 2 times x plus 3. We can take f of 2, which means that anywhere there was an x, we substitute in a 2. Now, here's a habit that is a pro tip. When you do this, always put brackets around where the x was. Even if you don't feel like you need them, always do it. And the reason for that is it's going to help you keep track of things that happen with negatives. And it's also going to help you make sure that you don't make a mistake with powers. You need to know that your negatives and your powers are not going to trip you up. So always put brackets and substitute your x inside those brackets. So f of 2 is 2 times 2 plus 3. F of 2 is equal to 7. G of 2 is 3 times 2 squared minus 4 times 2 plus 1/7. So this is 12 minus 8 is 4 and 1/7. Or if we want to be fancy, 29/7. And finally, h of 2, well, that's 1 over the square root of 2 minus 1. This in here becomes 1. The square root of 1 is 1. 1 over 1 is still 1. Okay, so we can evaluate a function at a particular value. All we're doing is we're substituting that value into x. You've done this before, you just haven't used this notation before. Now this notation, f of x, can be used interchangeably with y. When we write it with the f of x, it makes it easier to show what we're doing when we're substituting values into the function, and also later when we're doing calculus. Using the f of x notation is going to make things clearer. One of the most important concepts when you're learning about functions is domain and range. And here's how I remember them. This may not work for you, but this is what is in my head when I'm trying to remember what's what. I think of the word domain and I think of a king. A king has a domain. His kingdom is his domain. You know, Simba, everything the light touches is yours. That is Simba's domain. So that is a big horizontal space. So the domain has to do with the horizontal variable, which is usually x, but not always. But it's the horizontal variable. This is what can go into the function. If you're studying science and you understand dependent and independent variables, the domain is the independent variable. And then we have the range. Now the range is the dependent variable. And I think of an archer, he has range. Now, of course, the range when we speak about archery is actually the horizontal distance. But you point the arrow up, and so I think of how high it can go. That reminds me that the range is the vertical dimension. So domain, independent variable, horizontal dimension. Range, dependent variable, vertical dimension. So when we have a function is like a machine. It's a set of instructions, and that instruction set will take some input. The things which are allowed to be input are the domain, and then it will generate some outputs. The things that can be generated as an output are called the range. So we may be asked for some function to define the domain and the range, which means we need to figure out what can we put into this function for it to work and what's going to come out of this function. So for example, your function, we could imagine a little bit abstractly, is a toaster. What goes into your toaster? Well, bread goes into the toaster. If you put water into the toaster will break. It won't work. Water is not a part of the domain of your toaster function. But there are many types of bread which are. You could have white bread, whole wheat bread, multigrain bread. It will have to be sliced at a certain thickness to work, but that's our domain. What comes out of the toaster? Well, toasted bread. So we can have toasted white bread, toasted whole grain bread, toasted multigrain bread. Anything that can come in, we can have it come out toasted. That's the range of our toaster function. Now, in this example function here, not all x values are going to work. The reason not all x values will work is because this denominator cannot be 0. We can never divide by 0. So our denominators can never be 0. So this thing here, the square root of x minus 4, cannot equal 0. And furthermore, inside the square root, x minus 4 has to be positive because we cannot square root something if it is negative. So x minus 4 has to be greater than 0. So we have these two restrictions on the domain. X minus 4 must be greater than 0, and x minus 4 square rooted cannot equal 0. Now, because x minus 4 has to be greater than 0, we rearrange like an inequality, and we get that x must be greater than 4. This will keep the denominator positive. X cannot be equal to 4 because if it was, the square root would be 0. So x is strictly greater than 4. So that is the domain. The domain is that x is greater than 4. For the range, what can come out of this? Well, if we think about it for a minute, what we're going to notice is that this can never be equal to 0. Because if the numerator is non-zero, there's no value this denominator can be which will make this fraction equal to 0. And furthermore, because the numerator is positive and because the denominator cannot be negative, right? Because we are taking the positive square root. It's not a plus or minus square root, it's a positive square root. The denominator cannot be negative, so y cannot be negative. So the range of this function will be strictly greater than 0. So here's our answer for the range. So we have our domain is x is greater than 4, and our range is y is greater than 0, or f of x is greater than 0. 1 over x and the square root of x are the main things that lead to domain restrictions. So we had both of them here. We had our x in a denominator and we had our x in a square root. When you're working out the domain of a function, these are your biggest red flags. Is x in a denominator and is x in a square root? Because there will definitely be restrictions on x in these cases. But there are other cases where we also have restrictions on the domain. Some examples of these other cases include the log function, where x must be greater than 0. We have the inverse cosine function, where x must be greater than or equal to -1 and less than or equal to 1. Or we could have something a little fancier like the tan function. In this case, x cannot be half pi, 3 halves pi, 5 halves pi, 7 halves pi, any odd number of halves of pi. And this is using what is called set notation. X cannot equal 2k plus 1 times half pi. This means for any k, which is in the set of the integers. This z symbol means the integers. So what this is saying is, for no whole number k, can x be equal to 2k plus 1 times pi on 2. That's where the domain is restricted. All other x values will work. When we're giving the domain and the range, we have two ways we can write it. We can write with an inequality, or we can write with an interval, which comes from what is called set notation in mathematics. You need to understand both of these. The inequalities you should already understand well. We've done a whole video about them. The set notation is probably going to be new to you. So let's go over some basics. If we have this one-dimensional graph here, we can see that x can be equal to 2 or greater than 2. So x is greater than or equal to 2. Here's how we write that with set notation. So this says x is in the set. X is a member of the set. And here we have a lower bound of 2 and an upper bound of infinity. So it can be from 2 up to as high as you like. Now I want to point out that these brackets don't match. The square bracket means we include this boundary, so x can be equal to 2. The round bracket means we do not include this boundary. And whenever we're using infinity, we do not include infinity because infinity is not a number, it is a concept. There is no top number in this set. Okay, so we could have this here where x is greater than 2 but cannot be equal to 2. So you'll notice that in the set notation, what has changed is now instead of a square bracket, I have an ordinary rounded bracket here. So we have the same interval from 2 to infinity, but this time we do not include the 2. Here's another sort of interval. In this interval here, x can be greater than or equal to 0 or less than 2, or rather I should say and less than 2. And the way we put that in set notation is x is a member of the set from 0 to 2, where the boundary at the lower end, 0, is included, and the boundary at the upper end, 2, is not included. If there is no restriction, we say all real x values. That's not an empty circle, by the way, that's just a 0. So don't get confused by that. All x values are okay. Why do we say real? Because mathematics has real numbers and imaginary numbers. And you don't know yet, or don't need to know yet, what imaginary numbers are or how to use them. But you do need to know that when we say all x values, we say all real x values. We have to be specific. Similarly, if all the values are okay, we say x is a member of the set from negative infinity to positive infinity. There's one other possibility. In this case, we would say x is less than negative 1 or x is greater than or equal to 2. In set notation, we would say x is a member of the set from negative infinity to negative 1, not including negative 1, union with the set from 2, including 2, up to positive infinity. This union symbol, which you may remember from studying Venn diagrams, is a part of set notation. And it is equivalent to saying or. If you have the union of two sets, you can be in this set or in this set. Not to be confused with the intersection of the two sets where you must be in the overlap. The intersection is an and connection. The union is an or connection. So here we have looked at how to indicate with set notation simple inequalities, compound inequalities, other compound inequalities, and also the difference between a boundary that is included and a boundary that is not included. Transformations are one of the most important things for you to understand. The reason is you could be given a question that says, take this function, move it to this place, and stretch it in this way. So you would need to understand transformations in order to modify the function to transform it in that way. However, you could also be given a function and you can recognize what is the fundamental function here and what transformations have been applied. So you could say, well, I see it's a parabola. So in essence, it's y equals x squared, but then it's been stretched and shifted and moved, and now it's over here and it looks like this. And you use your understanding of transformations to be able to understand, okay, well, where has the vertex been moved to? How has the slope changed? All of these things are really easy to understand if you have a firm grasp of transformations. I want you to put extra attention into this topic right here, this may be one of the most useful things for the maths that's coming. If you understand this really well, future things are going to be easier. Functions can be transformed on the plane in a variety of ways. They can be reflected horizontally, they can be reflected vertically, they can be translated to the left or the right, up or down, and they can be scaled. They can be stretched and compressed horizontally, and they can be stretched and compressed vertically. You could imagine other transformations such as rotating a function. We don't touch rotations in this course, and the reason is if a function passes the vertical line test but you rotate it, at some point it may cease to be a function. And so for that reason, we don't talk about rotations when we're studying functions. We would talk about rotations if we were just studying relations in general. So if we want to translate something up or down, we add or subtract a constant. If we want to translate something left or right, we also add or subtract a constant. So what's the difference here? Well, in one case, we take the function and then we add or subtract something onto it. In the other case, for a horizontal, if we want to change in the x variable, we actually add or subtract from the x value inside the function. If we want to stretch or compress it vertically, we multiply the whole function either by a number bigger than 1 to stretch it or a number between 0 and 1 to compress it. If we multiply it by a negative number, we will flip it vertically. If we want to stretch or compress it horizontally, we will multiply inside the brackets. We'll multiply the x variable itself. And again, if we multiply inside the brackets by a negative number, we reflect it left to right. Now, there are some nuances here. The first thing that we've looked at is when we're affecting the y value, we're doing something to the entire function. We're adding or subtracting to the entire function, or we're multiplying or dividing to the entire function. When we want to modify the x value, we're working inside the brackets. We're working on the argument or the parameter or the variable of the function, right? We're doing it to the x. But notice this as well. When we're working on the y, if we want to move up, we add x. And if we want to move down, we subtract x. When we're working on the x, if we want to move in the positive direction, we have to subtract our variable. If we want to move in the negative direction, we need to add our variable. So for the y, adding a positive number moves it in the positive y direction. But for x, adding a positive number moves it in the negative x direction. It's like it is flipped. There are really good reasons for this. I'm not going to explain them because it will probably confuse a lot of people. So I just want you to think about it very simply. When we work on the y, we work outside the brackets, and to go in the positive direction, we add a positive number, and to go in the negative direction, we add a negative number. When we want to move in the x direction, we work inside the function, and to go in the positive direction, we have to add a negative number, and to go in the negative direction, we have to add a positive number. It's opposite. The same applies for stretching and compacting. If we want to stretch something vertically by a factor of 2, we multiply the whole function by 2. If we want to stretch something horizontally by a factor of 2, we divide inside the brackets by a factor of 2. To stretch it horizontally, we divide. To stretch it vertically, we multiply. The opposite is true for compressing. If we want to compress a function, we divide the whole function. If we want to compress it horizontally, though, we multiply inside the argument. We multiply the value of x. Again, I'm showing the same pattern. To modify the y, we work on the whole function. To modify the x, we work inside the brackets. To make it bigger in the y direction, we multiply it. To make it smaller in the y direction, we divide it. But for x, to make it bigger, we divide it. And to make it smaller, we multiply. Because the y ones are very intuitive, they make sense. We do something to the whole function and we do it in the direction we want. But for the x, it's the opposite. We do it inside the function and we do it the opposite to what we might expect is the result we want. This can be a little bit confusing at first until you have internalized and memorized those relationships. To illustrate this, what you can do is you can go to Desmos, you can make up some function. I'm going to say x cubed minus 2x plus sine x. No, you know what I'm going to do? I'm going to do times sine x. Look at that. Isn't that funky looking? Here's what I want to do. I've written in this, you can write this into a times, so I've defined f of x here, and then I've written a times f of, inside we have x minus h, that's our horizontal transformation, times c. This is our horizontal stretch, our scale factor. And then we have plus k, which is our vertical transformation. And we have times a, which is our vertical scale factor. I'm going to put one more set of brackets there. Now, we have this option to add sliders for a, c, h, and k, and I'm going to add sliders for all of them. So here's our function if a, c, h, and k are all equal to 1. Let's work inwards. The outermost variable is a, and this is our vertical scale factor. So you can see that when it's bigger, we're stretching this vertically, and when it's smaller, we're compressing this vertically. Now you notice that from 0.1 to 0, we don't see much happening, but if we make this smaller, you can see more and more compression happening. Okay, so a is our vertical scale factor. We can make it a number bigger than 1, we'll stretch it, and a number smaller than 1, we'll compress it. Similarly, a negative number, we'll flip it upside down. Then we have k, which is our vertical translation. So by moving k, I'm going to make here, a can be 0.01. And I'm going to move k between negative 100 and 100 with a step of 10. And so here we can see, we can move it down, we can move it up. Whichever way k goes, positive or negative, is the direction that the function moves. Then we have c, which is our horizontal scale factor. The bigger c gets, the more squashed up our function becomes. And the smaller c gets, the more stretched it gets. So c between 0 and 1 is going to start to stretch it right out. And if c becomes negative, we flip it around the x-axis. And if we modify h, you can see that we move from the left to the right. There are some subtle differences here to notice. So I put brackets around all of this. So the a gets multiplied by all of this. If I remove those brackets, now the a only applies to the function, and it does not apply to k, the vertical translation. Okay, so I stretch a. If the function's centered at the origin, it stretches from the origin. If I move the function up and now I stretch a, it's no longer stretching from the origin, now it's stretching from wherever k is. Similarly, if I get rid of these brackets here, now when I shift h, the whole function moves, but when I change c, you'll always notice that it's going to stretch from the y-axis. It will always get closer to the y-axis or further from the y-axis. When I was learning functions, we just had to draw 100 of them to see what difference it makes to change a variable. What you can do these days is you can put in a function, any function. You don't have to copy my function, and then put in this rule, add these sliders, and you can very easily experiment and see what effect each of these variables has on the function that you've chosen. So I strongly recommend that you have a play with this and see what you can learn for yourself about transformations on the plane. Let's stop here and go through a bunch of questions to check if we've understood what we've covered. So, determine whether the following relations are functions. For a relation to be a function, it means that there cannot be an x value that points to two different y values. So in this first set, every x value has a different and unique y value. So this is a function. In this second set, we can see that when x is 1, the y value can be 2 or 4, and that means this is not a function. Here, y equals x squared, that's a parabola, and a parabola will pass the vertical line test. So this is a function. X equals y squared, this is also a parabola, but it's on its side, and this will fail the vertical line test. So no, this is not a function. Which of the following mappings represent a function? A list of students and their student ID numbers. Well, you cannot have two student ID numbers for one student, usually. So I would say that yes, this is a function. A list of students and their favorite colors. I could imagine that a student may have more than one favorite color. So I think this is not a function. But if we force them, if we said you can only pick one color, then it would be a function. A vending machine where you enter a code and you get exactly one snack. Can the same code give you two different snacks? No. This is a function, but imagine if they refill the vending machine next week and they put in an extra row of water where previously there had been orange juice. And so now the code that used to give you orange juice gives you water, in which case you enter the same code, you get a different snack. But it's never the case that the one code could give you two different values at the same time. That's never the case. So it is a function. A vertical line test is applied to a graph. Which of the following describes a function? Well, the vertical line cannot cross the graph at 2 points if it is a function. The vertical line crosses at exactly 1 point for all x values. This would be a function. The vertical line never intersects the graph. That is possible for a function. You can have a vertical line on a function where it never touches. So as an example, we could take a function which is a hyperbola. So this sort of shape here, and if you have a vertical line here, it doesn't touch the function. If the vertical line never intersects the graph no matter where you put it, then you don't have anything. It technically passes the vertical line test, but I wouldn't call it a function or a relation. It's just nothing. You might have the function f of x equals 0. This would still be something. It would be a horizontal line. If you have nothing, you don't have anything. Domain and range questions. Find the domain and range of the following functions. So for A, the domain, if the function is x squared minus 4, there's no value of x that we are not allowed to square and subtract 4 from. So the domain is all real x. And the range, x squared is always going to be positive, which means that we're subtracting 4 from a positive number. So if that positive number, if it was 0, we could get down to -4, but we can never get lower than that because this number has always got to be 0 or greater. In terms of the graph, we have a parabola that's being shifted down 4 spots. So the range is anything greater than -4. So we can say y is on the interval from -4 to infinity. For b, 1 over x plus 2, we have an x in a denominator. So we know there's a restriction because that denominator can't be equal to 0. So we have that x plus 2 does not equal 0, which means x cannot equal -2. So I would write it like this. X is on the interval. We can have all real x except -2. So we can go from -infinity to -2, and we can join that with the set from -2 to infinity. The only thing that's excluded is we're not counting the -2. For the range 1 over x2, this is going to be a hyperbola, so it's going to go as high as we want, and it's going to go as low as we want, but it will never equal 0. We can't put in any value of x that will make 1 over x plus 2 equal to 0. So we'll have a similar thing for the y, where the y is from -infinity to 0, union with 0 to infinity. C, the square root of x minus 3. So remember, inside a square root, we have to be careful because if we get a negative number inside the square root, we're in trouble. We can't square root it, which means that x minus 3 has to be greater than 0, or in other words, x has to be greater than 3. I should note, it can be equal to 0. We can take the square root of 0. So we could say x is greater than or equal to 3, or we can write it like this. X is on the interval from 3 to infinity. For the range, we can get any number that is 0 or greater. So when we take the positive square root, it could be the square root of 0 is 0, but then it will have to be bigger than that. As a graph, this thing is going to look like the top half of a horizontal parabola. And so that means that our range will be x is greater than or equal to 0, or we could write it as x is on the interval from 0 to infinity. Either of these is fine. You don't have to do both. You just have to pick whatever one makes most sense to you. You have to understand both. Okay, this last one is an absolute value. We haven't explicitly covered absolute values yet. We're going to cover them in a future lesson. I deliberately delayed them because I wanted to say what a function is before we spoke about what an absolute value function is. Suffice to say that this one is going to look like a giant V shape, and the point of it is going to touch at x equals 5. So we can see that all values of x are fine. So for D, the domain is all real x, while the range is only y values greater than 0 or equal to. So the range, we say y is greater than or equal to 0. And I've just realized up here I put x. These should be y because it's a range. It should be f of x or y, not x. So that was an error. Should say y for range. Okay, question 5. We have this function here given. F of x equals 2 over x squared minus 9. So we want to find the domain and we want to justify why certain values are excluded. The restriction on the domain here is that x squared minus 9 cannot equal 0, which means that x squared cannot equal 9, which means that x cannot equal plus or minus 3. There are two values of x that cannot be equal to 2, because either of those, if we square them, we get 9, and if we do that minus 9, we're going to get a denominator of 0. If we graph this function, this is what it's going to look like. And what you'll see is that there are what we call vertical asymptotes. We could draw in a vertical line here at x equals 3. Let me do that. And we could draw in another one at x equals -3. And the function will never touch these lines. If we zoom in, there's always going to be a gap. We will never be at these lines. And so this is why when we define the domain, we need a restriction to specify that x can never equal plus or minus 3. And I would define the domain like this. Domain is x is of the set from -infinity to -3, union -3 to 3, union 3 to infinity. That is how I would define the domain. You could also say x is less than -3, or -3 is less than x is less than 3, or 3 is less than x. These two lines are giving the same definition. I prefer to use set notation because I find it easier to read. I find this requires me to think harder to understand. The range of f of x is x squared plus 3 is given as 3 to infinity. Explain why the range cannot include values below 3. F of x equals x squared plus 3. If we're going to graph that, we're going to have a parabola that's being shifted up by 3. We have a parabola that's been shifted up by 3, which tells us that the y values we can get are 3 or greater. This is why the range is y is a member of the set from 3, including 3, up to infinity. We cannot get any y values below 3 because the graph is not down here. There just is no value we can get down here. All the values are up there. If we start with the function x squared, how do we transform it to get these other functions? We're going to go through each one, and for each one, we're going to describe the transformation, and then we're going to check it on a graph. For this first one, we can see that it's being shifted up by 2. Inside the brackets, we have a horizontal transformation. It's a -3, which means we're moving in the positive direction by 3. So this parabola is going to have been moved to the right by 3 and up by 2. And so the vertex, instead of being at the origin, is now at the point 3, 2. And we can see that right here, we have the vertex at the point 3, 2. For the second one, we can see that it's being flipped upside down because we've multiplied the function by a negative. And then it's been shifted up by 5 afterwards. So that means that our parabola is going to have its vertex here at 0, 5. And it's going to be upside down. And here you can see the vertex at 0, 5 on an upside down parabola. For the third one here, we have 3 transformations. Firstly, we can see that it's being shifted to the left by 1 because we add 1 to the x, which means we're moving in the negative x direction. Then we have stretched the whole parabola to be twice as tall or twice as steep. And finally, we have shifted it down by 4. So on our graph, our vertex is going to be at -1, -4, and our parabola is going to be quite steep. So here we have it with the vertex at -1, -4. And just for comparison, watch when I remove this scale factor, it becomes less steep. So it becomes steeper when we multiply it by 2. For the last one here, we are multiplying it by 1/2. That's going to compress it. It's going to make it less steep. And then we're shifting it down by 6. So it's going to be something like this with a vertex at 0, -6. So here you can see the vertex at 0, -6. And just for comparison, if I get rid of that factor of 1/2, you can see it's a little bit steeper. So having that factor of 1/2 made it more shallow, made it less steep, squashed it down. Question 8. So this is the same thing, but instead of starting with x squared, we're starting with x cubed. Firstly, we can see we're adding 2 to the x, which means we're moving 2 in the negative x direction, and then we're subtracting 1 from the whole function, which means we're moving down by 1. So our graph is going to look something like this, where this turning point here will be at -2, -1. So here you can see our turning point at -2, -1. For B, we've moved it 4 in the positive x direction, and then we've flipped it upside down and stretched it by a factor of 2. So that means instead of crossing at the origin, it's going to cross at x equals 4. Instead of going from the bottom left to the top right, it's going to come down from the top left. It's going to be quite steep, and it's going to go out to the bottom right. This is something of what our function is going to look like. And here you can see with our x-intercept at 4, 0. Last one in question 8. In this case, we can see that we are multiplying by 1/3, which is going to squash and make less steep our cubic function. And then we're shifting it up by 7. So it's still going to cross the y-axis, but it's going to be less steep, and it's going to cross at y equals 7. So we're going to have a normal cubic function, except it's shifted up to cross at 7, and it's going to be less steep than usual, a little bit more rounded. And we can see that just here, crossing the y-axis at 7, and it's a little less steep. If I get rid of that factor of 1/3, you'll see it gets steeper, like that. For question 9, here we're shifting it by 2 in the positive x direction. We're flipping it upside down, we're stretching it, scaling it by a factor of 3, and then we're going to move it by 5 in the positive y direction. If we start with y equals the square root of x, first we can shift it by 2 in the positive x direction. Then we flip it upside down, and then we stretch it by a factor of 3, and then we move it up by 5. And this is what we get. And if we zoom out, we can see a bit more. It is really just a sideways parabola. We're just taking 1/2 of it. Okay, find the equation of a function that results from shifting this left by 4 units, stretching it vertically by a factor of 3, and reflecting it across the x-axis. Oh boy, so we got a lot going on here. So we start with f of x equals x squared. We want to shift it left by 4 units. That's the negative x direction, which means we're going to have to add 4 inside the function. So it will become f of x plus 4. Then we want to stretch it vertically by a factor of 3. So we just multiply the whole thing by 3. 3f of x plus 4 equals 3x plus 4 squared. And then finally, we want to reflect it across the x-axis, which means we're flipping it upside down. So it will become -3f x plus 4 equals -3 times x plus 4 squared. Now I want to just do a little bit of extra work here because I want to show you something. If we expand the right-hand side here, we get -3 times x squared plus 8x plus 16, or in other words, -3x squared minus 24x minus 48. Okay, let's have a look at something. F of x equals x squared. Now, what I want to graph next is -3x squared minus 24x minus 48. So here we have the function. It's being shifted to the left by 4 units. It's being flipped upside down and stretched by a factor of 3. If I say -3 f of x plus 4, notice that this is exactly the same as the one we just drew. The reason I'm showing you this is I want to make it clear that what I've done on the left-hand side, where I've applied the transformations in function notation, is exactly the same as what I've done on the right-hand side, where I've done the transformations, I've expanded the brackets, collected like terms, simplified everything. So the key thing here is to understand this is what the question's looking for. This is your answer. You could get away with leaving it in this form, but I also want you to understand how I've done it on the left-hand side here. I want you to be able to read this just as easily as you can read this. They're very similar if you think about it. F of x is x cubed. We want to compress it horizontally by a factor of 2. Now what we know is that to compress it horizontally, we want to multiply by that factor. So we now have f of 2x equals 2x cubed. We want to reflect it in the x-axis, so we're making it upside down. So negative f of 2x, which is -2x cubed. And then we want to shift it downwards by 3 units. So negative f of 2x minus 3 equals negative 2x cubed minus 3. And just to expand out the right-hand side, that's going to be negative 8x cubed minus 3. And so the transformed function, which I'm going to call g of x, that is negative f of 2x minus 3, or in other words, g of x is equal to negative 8x cubed minus 3. Now, I want to point something out here. Here's our original function. If we apply these transformations, here is the new function. There's something really important to point out here, though. We could reach this same transformation by doing something different. Instead of compressing it by a factor of 2, flipping it and shifting it down, what we could do is we could scale it vertically, not horizontally, vertically by a factor of negative 8. That will flip it and stretch it and then shift it upside down. So have a look at this. As I said, we could go negative 8f of x, that's our vertical shift, and then we move it down by 3. And what you can see is that that's exactly the same as the other transformed function we had. And what this is telling us is we can get to the second function through more than one combination of transformations. But in either case, what we are graphing is y equals negative 8x cubed minus 3. These are all the same function. They are what you get when you take this function and you apply this combination of transformations, or you apply this combination of transformations. They're equivalent in this situation. Okay, let's take stock here. We said, what is a relation? Then we looked at what are the types of relations. They were many to many, many to one to many, one to one. And we realized that functions are relations that pass the vertical line test. So they end in 2, 1. They can be 1 to 1, or they can be many to 1. They end in 2, 1. Functions have this f of x notation. A function has a domain, a set of x values which are allowed to go into it, and it has a range, which is the set of y values that it's possible to get out of it. And we can transform a function. We can move it up and down, we can move it left to right, we can compress it or stretch it horizontally, and we can compress it or stretch it vertically. And we've looked at all of those. Now, we're going to go back to function notation a little bit, because that's what we're going to be using to explain function composition and to explain even and odd functions. You would rarely cover all of this in one lesson in school, but because you can pause this, you can replay it, you can revise it later. I'm giving you lots of practice questions in the worksheet. I trust that you are going to be able to learn all of this, and it's going to make more sense as you start applying it in new situations and as you see it in class as well. Function composition. What does that mean? To compose something is to take parts and join them into a whole. So function composition is looking at different ways to take functions and join them together. We can use the 4 basic arithmetic operations, but we can do it in other ways. I'm only going to teach you one other way today. In fact, that's the only other way that's going to matter in advanced math. If you study higher levels of more abstract mathematics, you will see that you can combine functions in any way that you can think of a rule to follow. But we're just going to stick with the 4 basic arithmetic operations and one more called nesting. So in order to illustrate this, I've chosen 2 functions. We've got f of x is 1 over x minus 2, and g of x is 3x squared. If we're adding them, f of x plus g of x is just f of x plus g of x. Because this is a fraction, we add them like this, and we can simplify, but that's all it is. There's nothing here is going to be new or different. I'm just teaching you that if we have f of x plus g of x, we do f of x plus g of x. I want to point out that addition of functions is commutative. This is like all addition, where f of x plus g of x is equal to g of x plus f of x. The order in which we do it is not important. Function subtraction, f of x minus g of x. Well, that's f of x minus g of x. Put it all into one fraction, simplify, yada yada, easy. But I do want to point out that this is not commutative, because g of x minus f of x gives us a different answer. Notice this numerator is 3x squared, negative 3x squared plus 6x minus 1. Here we have the opposite. We have positive 3x squared minus 6x squared minus 1. These are not the same. Subtraction is not commutative. F of x minus g of x is not the same as g of x minus f of x. Multiplication, f of x times g of x. Well, we just take f of x and we multiply it by g of x. Simple. Multiplication is commutative. F of x times g of x is the same as g of x times f of x. Simple. 2 times 3 equals 3 times 2. No surprises. And division. F of x divided by g of x is f of x divided by g of x. And we can just simplify our fraction and get our answer. This is not commutative. G of x divided by f of x gives us a different answer to f of x divided by g of x. Just like 10 divided by 2 gives us 5, but 2 divided by 10 gives us 1/5. Division is not commutative. And finally, we get to the new operation called nesting. So instead of doing f of x, we can do f of g of x. So f of x was 1 over x minus 2. Now everywhere that we had x, we replace it with g of x. So this becomes 1 over 3x squared minus 2. Now, nesting is not commutative. Maybe you are lucky sometimes and it is, but as a rule, it is not. So if we take g of f of x, now g of x was 3x squared. So where the x was, we put f of x. We have 3 times this squared, or in other words, 3 over x minus 2 squared. These are not the same. Nesting is not commutative. So we've looked at adding functions, subtracting functions, multiplying functions, and nesting functions. All of these operations are important. Some functions follow specific patterns and have special properties. These are even functions and odd functions. Not every function is even or odd. Just like the number 2 is even, the number 3 is odd, the number 2.5 is neither even nor odd. In this way, you can have functions which are even, functions which are odd, and functions which are neither even nor odd. Let me give you some examples. Even functions can be understood as functions where the graph is symmetric about the y-axis. In other words, if you folded it along the y-axis, the two halves would line up, okay? It's symmetric around the y-axis. That should be pretty easy to understand. Odd functions are functions where if you folded this and then flipped it upside down, it would line up. A type of symmetry, but it's not so simple. You can't fold it in any one direction and have it line up. You have to fold it horizontally and then vertically. This is an odd function, right? These are all examples of odd functions illustrated here. Any function that doesn't fit one of these specific criteria is neither even nor odd. Now, simple fact that's worth knowing is that for any polynomial, right? This is what a polynomial looks like. It's a series of powers of x added together. If all the powers of x are even, right? This is x to the 0 here. If all the powers of x are even, you have an even function. If all the powers of x are odd, you have an odd function. But not all functions are polynomials. For example, you can have trig functions, which can be even or odd or neither, but you cannot just look at the powers of x to figure it out. Let's have a look at some of these polynomials. Here we have all even powers. Remember, x to the 0 is still an even power of x. And we have a beautiful symmetric function. Here, all of our powers are odd. Remember, this is x to the 1. And we have quite an interesting odd function where if we folded it this way and then flipped it upside down, it would line up perfectly. And then here's one where we have odd powers and even powers mixed together. And you can see that this one is not symmetric around the y-axis, and it's not going to line up if we fold it across the y-axis and then flip it around the x-axis. This is neither even nor odd. Powers are a mix of even and odd, but that's just for polynomials. So if a function's not a polynomial, how can you really know if it's even or odd? Here are the definitions. If you take your function and you put in a negative x, and you simplify it and you get back to the original f of x, that means it's even. That means that whatever's happening on the negative x half of the plane is equal to what's happening on the positive x half of the plane. However, if you put in that negative x and you get the negative of the original function, it is odd, which means that what's happening on the negative x half of the plane is upside down from what's happening on the positive x part of the plane. That's an odd function. Anything that doesn't give you one of these results is neither even nor odd. So let's have a look at some quick examples. If we take our f of x from before, we do f of negative x, we substitute a negative x in there, and so we get negative 1 over x plus 2, or 1 over negative x minus 2. This is not the same as f of x, and it is not the negative of f of x. So this function is neither even nor odd. If we take 3x squared and we plug in negative x, that negative x just cancels itself out. We get back to 3x. In this case, g of negative x is equal to g of x, so g of x is an even function. For something a little bit different, if we have h of x is sine x, and we do h of negative x is sine of negative x, something we need to know about the trig functions is that sine of negative x is equal to negative sine of x. In other words, negative h of x. So h of negative x is equal to negative h of x, which means h of x is odd. These are just a few quick examples. We're going to do more in a moment, but I wanted this so that you could see one example where it's odd, one example where it's even, and one example where it's neither. All right, let's get into the fun stuff. Here we are doing function composition. F of x plus g of x is going to be 2x plus 3 plus x squared minus 1, which is going to be x squared plus 2x plus 2. F of x minus g of x is 2x plus 3 minus x squared minus 1. Now you'll notice when I was adding them, the brackets did no work for me. I didn't need to put them there, but I do it as a habit because they are doing work for me here. I need to have them here because I need to remember that this negative 1 is going to become a positive because of this minus sign out here. So in this instance, we're going to have negative x squared plus 2x plus 4. F of x times g of x will be 2x plus 3 times x squared minus 1, which will give us 2x cubed minus 2x plus 3x squared minus 3, which will give us 2x cubed plus 3x squared minus 2x minus 3. In this step, I have not done anything except change the order in which I write them. This is me being OCD, but it's a habit I recommend to you. In the future, this will make things easier. You're going to put the largest powers of x first, and then continue in descending order until the lowest power of x. F of x divided by g of x is 2x plus 3 over x squared minus 1, and we can't actually simplify this. We're done already. There's one caveat that they add, which is a really important one, which is g of x cannot be equal to 0. So, thinking of domain and range, we can see here that x cannot equal plus or minus 1, because if it did, x squared minus 1 would be 0, this would explode and destroy the universe. Okay. Now we get to the fun ones. We have 4 examples just of nesting, and we're going to do different combinations with the 3 functions they've given us. So f of g of x is going to be 3 times g of x minus 2, or in other words, 3 amounts of x squared plus 4 minus 2, 3x squared plus 12 minus 2, so plus 10. G of f of x, so we have f of x squared plus 4, which is going to be 3x minus 2 squared plus 4, which is 9x squared minus 12x plus 4 plus 4, or in other words, 9x squared minus 12x plus 8. Now, h of g of x means we're doing the square root of g of x plus 1, which is the square root of x squared plus 4 plus 1, or in other words, the square root of x squared plus 5. And there's not really much we can do with that. We're done. And finally, f of h of x, which means 3 of h of x plus minus 2, 3 of square root of x plus 1 minus 2, or in other words, 3 root x plus 1 minus 2. And we can just leave that there. That is done. If you want to challenge yourself, see if you can figure out what is f of g of h of x, or g of f of h of x, or h of f of g of x, or h of g of f of x. There are so many combinations, and they're all going to give you different answers. So there's lots of practice you can do just with these 3 functions right here. Okay, f of g of x was number 5. So this is f of g of 2, which is 3 of 2 squared plus 10. 2 squared is 4 times 3 is 12 plus 10 is 22. And then g of f is this guy here. So g of f of negative 1 is 9 times negative 1 squared minus 12 times negative 1 plus 8, which means 9 times 1 plus 12 plus 8, which is 29. Cool. Now we have some questions. Testing for even or oddness, evenness or oddness. This is a polynomial, and the powers of x are all odd. This is an odd function, but you will probably not get full marks if you just say that. So let me show you what you have to do. F of negative x equals negative x cubed minus negative x equals negative x cubed plus x equals negative f of x. So if f of negative x equals negative f of x equals negative x cubed minus x, therefore it is negative f of x. If f of negative x equals negative f of x, we say therefore f of x is odd. That's a lot more work than just noticing that the powers are all odd, but you got to do what you got to do. Okay, question 12. We can see we have a polynomial where the powers are even. We have an even function. We know it's an even function, but we want to get full marks, and some of those marks are for our working out. So how do we get those marks? 12. G of x equals x to the 4 plus x squared. G of negative x equals negative x to the 4 plus negative x squared. A negative to an even power becomes a positive, so we have x to the 4 plus x squared, which is g of x. Since g of negative x equals g of x, therefore g of x is even. We already knew that. Okay, question 13. Question 13 I like because it's not obvious immediately whether it's going to be even or odd. Let's find out. H of negative x is equal to negative x over negative x squared plus 1, which will become negative x over x squared plus 1, which is negative h of x. So if h of negative x equals negative h of x, we can say therefore h of x is odd. Question 14. We have a polynomial. All the powers of x are odd. We know it's going to be an odd function. How are we going to show that so that we get full marks? J of negative x is negative x to the 5 minus 2 times negative x cubed plus negative x. A negative number to an odd power gives us a negative answer. So we have negative x to the 5 plus 2x cubed minus x, which is minus x to the 5 minus 2x cubed plus x, which means it's the negative of j of x. Since j of negative x equals the negative of j of x, therefore j of x is odd. Now we have one more here, k of x, which is e to the x plus e to the negative x. K of negative x is e to the negative x plus e to the negative x. Of course, that double negative becomes a positive, and so this becomes that term, and this becomes that term, and we're back to k of x. Because k of negative x equals k of x, therefore k of x is even. Interestingly, none of these examples here failed to be even or odd. Every one of them was one of even or odd. But you will find sometimes they will fail a test, and you will not be able to get f of negative x to equal negative f of x or f of x. We've done a lot today. We've looked at what is a relation. A relation is any rule connecting at least two variables, x and y. What are the types of relations? Well, we sorted them into categories: many to many, many to one, one to many, and one to one. And we said, what is a function? Well, a function is a relation that passes the vertical line test. In other words, it's a relation that ends in 2, 1. It's either 1 to 1 or many to 1. How do we evaluate a function at a specific value? So instead of f of x, we write f of 2, and then we substitute the 2 everywhere there was an x. What are domain and range? Well, domain are the values of x that we're allowed to put into our function without breaking it. And range are the values of y that our function is capable of producing. How do we read and write interval notation? So we looked at how we could say x is greater than or equal to 2, and how we could rewrite that and say x is a member of the set from 2, including 2, up to infinity. How to transform a function on the plane. So we looked at transformations involving shifting the function up or down, or left or right. We also looked at transformations that were compressing or stretching it horizontally, compressing or stretching it vertically, and we also looked at flipping it vertically or flipping it horizontally. How to compose functions with arithmetic and nesting, so adding them, subtracting them, multiplying them, dividing them. We also saw that addition and multiplication are commutative. You can do them in a different order and you get the same answer, whereas subtraction and division are not commutative. If you swap the order, you get a different answer. And we also looked at nesting, where you put one function inside the other function. And we saw that this is not commutative. In most cases, you will get a different answer if you nest in a different order. And lastly, we looked at what is an even function, what is an odd function, how do we tell if a function is even, how do we tell if a function is odd. So we've covered a lot of theory today. Please practice and complete the worksheet as a practice test. It's really important to practice what you know, figure out what you know, identify if you're struggling with any of the concepts. I think the hardest topics here are going to be identifying domain and range and also transformations on the plane. You may also have some trouble with function composition once it gets complicated, once there are many parts. And you may also have trouble telling if a function is even or odd. But I think those should be pretty routine for you if your algebra is strong. And the conceptual challenges here are going to be thinking thoroughly about domain and range and thinking carefully about transformations, particularly the order of different transformations. What we've covered today is very theoretical. I think of them as very big brain concepts, and it will make later work easier if you understand this stuff well. And what we're doing right now is we're laying foundations so that we have the language and the notation that we need in order to learn calculus. Anything you're struggling with, practice. Reattempt any examples or worksheet questions that you found difficult. Find additional practice questions from your textbook, from your teacher, from your tutor, or even from AI. Just use discretion if you're using AI. Do not trust that its questions will make sense. Do not trust that it can give you the correct answer to those questions. Thank you very much for checking out this lecture today. I've had a lot of fun making it. This is one of my favorite topics to teach, and I hope that you found it interesting to learn it as well.